Okay, welcome everybody. Today's head lunch. Somewhat unusual location, Pratt. I think in the next few weeks, next maybe 3 or 4 weeks, we will be here, and then we go back to Philips for good. That's why we have this funny camera here. So today we have 2 speakers. Katie Auchettl, did a good job. She's going to tell us about the gamma ray and X-ray emission from Supernova Remnant MSH 11-61A. And after that we follow with Dongwoo. I think he's somewhere around. And I hope so. His computer is here. And Dongwoo will tell us about scaling relations, X-ray scaling relations in early type galaxies. So, please.
All right, g'day everyone. Thank you for coming. So I'm going to tell you about the high energy emission from this beautiful object here, seen in purple. I guess it's a bit hard in these lights, called MSH 11-61A, and it's a supernova remnant. It's very close to my heart. Okay, so as many people know, cosmic rays come from everywhere in the universe, and we can measure their flux over many decades of energy. It can't be a cosmic ray talk without that plot there, right? So there are 2 types of cosmic rays. There are primary cosmic rays and secondary cosmic rays. So primary cosmic rays come from particles that are accelerated by astrophysical objects, such as supernova remnants. And then there are secondary cosmic rays, which arise from the interaction of the primary cosmic rays with interstellar medium or interstellar radiation fields. The distribution of cosmic rays, as measured at Earth, can be described by a relatively featureless spectrum, as shown here, and it extends over multiple decades of energy, so from 10 to the 10 to the 10 to the 20 eV. If you notice that I've pointed out here, because it's a bit hard to kind of reach as I've got the camera needs to be here, you can see that there is actually 2 breaks in this spectrum. There is one at the knee of the spectrum at 10 to the 15 eV, and one at the ankle at 10 to the 18. These spectral breaks are actually intimately related to the origin of cosmic rays, with particles coming with energies below the knee correspond to galactic origin cosmic rays, while ones above the ankle are actually thought to be extragalactic. So supernova remnants are actually the leading candidates for the origin of cosmic rays below the knee. This fact arises from 2 main points of evidence. The observed energy density of cosmic rays at Earth can naturally be explained by supernova remnants if one assumes that 1 to 10% of the energy of a supernova remnant goes into accelerating particles. While from early radio observations, it appeared that supernova remnants are actually sites of particle acceleration. The radio emission that was actually observed from these objects arises from synchrotron radiation, which can only be emitted from a population of non-thermal, a power law population of non-thermal electrons being accelerated. The spectral index that one gets from a radio emission from a supernova remnant is approximately 2, which actually agrees with an uncertainty with the spectral index of the cosmic ray spectrum measured at Earth. But more importantly, the index of 2 actually corresponds to the spectral index that's derived from diffusive shock acceleration, which is thought to be the mechanism that actually causes this acceleration to occur and get these particles up to these energies. But I'll talk a little bit more about that a little later. But before I go on, I should actually tell you what a supernova remnant is, right? Apart from just showing you these beautiful pictures. So a supernova remnant results from a massive fuel-depleted star collapsing under its own gravity, or from a white dwarf star that goes supernova when the amount of mass accreted from a nearby companion star reaches the Checker-Sandra limit. The energy from this explosion is partially converted into kinetic energy, which forms an expanding shock wave of ejecta in interstellar medium called the forward shock. As this ejecta-driven shock wave sweeps up mass, it actually slows down, resulting in a back pressure on the expanding ejecta. And this actually forms what is called a reverse shock. The reverse shock heats up the ejecta, and what we see in different wavelengths and what produces these beautiful pictures that we are lucky to have is what is called a supernova remnant. So apart from actually being able to sweep up mass, the forward shock has the ability to actually accelerate particles. as the shockwave propagates, particles will actually scatter back and forth across the shock in the form of magnetohydrodynamic waves that have formed on either side of the shock front. This process is this scattering back and forth is called diffusive shock acceleration. And the particles experience this will gain energy every time it crosses the shock, and until their mean free path of scattering is large enough that they can actually escape the shock and propagate to us. It was discovered relatively simultaneously by a number of authors in the late 70s that the shockwave can actually naturally enhance the effects of cosmic ray acceleration. And this enhancement actually naturally resulted in a power law energy distribution of particles. The energy distribution of the particles derived from this mechanism actually has a spectral index of 2, that magic number of 2 again. And if you remember from my previous slide, this actually is corresponds. It's similar to the one that of similar to the spectral index of the cosmic ray spectrum measured at Earth, and also for the what the radio spectrum of supernova of radio emission coming from supernova remnants. So actually, diffusive shock acceleration has been applied from a theory onto supernova remnants to see what's happened, to see if it actually works, and it actually worked really well. By assuming basic supernova remnant parameters such as a modest acceleration efficiency, diffusive shock acceleration has actually been used to calculate what the maximum energy that supernova remnants are expected to accelerate up to. It was found that supernova remnants can accelerate particles up to 10 to 100 TeV, which is very close to the knee of the cosmic ray spectrum. Since the advent of high resolution X-ray observations, this has actually been confirmed that supernova remnants can actually accelerate particles up to these high energies. For example, here is a lovely picture from Chandra, which shows X-ray synchrotron emission coming from the shock front, seen here that is highlighted. This actually can only occur from a population of multi-TeV particles. And this supernova remnant is one of the poster child for it, and it's called SN1006. So it's very beautiful for that. So essentially you can say is that supernova remnants are actually cosmic ray accelerators. So now that we know that supernova remnants can actually accelerate particles, the next question that naturally comes to mind is what emission do we expect to observe when things are being accelerated? So when particles are accelerated, they will actually lose energy via a number of different mechanisms, and which will either produce radio, X-ray, or gamma rays, depending on which mechanism you're interested in, or which one, energy range that you are focusing on. For this talk, I will focus on gamma ray emission for this. So there are actually 2 main mechanisms that produce gamma rays. There is leptonic emission, which includes inverse Compton scattering and non-thermal bremsstrahlung, and there is hadronic emission, which is pion decay, which results from the decay of a neutral pion into 2 photons. And so these are the main mechanisms that we're interested in. But for anyone who's actually done any modelling of these type of emission mechanisms with supernova remnants, one thing that you learn very quickly is suddenly that these emission mechanisms actually produce very overlapping signatures in the same energy band. So then the next question is like, well, how are we going to differentiate between these different mechanisms if we only have data in that energy range, right? So, but there's actually a really nice kind of way to do this. So the one way we can actually do this is actually look at supernova remnants that are interacting with molecular clouds. The reason why is that these are actually really good candidates for detecting and studying gamma ray emission coming from pion decay, because molecular clouds are big sources of protons, so you should expect a more bias towards pion decay with that. The Fermi-Lat satellite, which is a gamma ray satellite, has detected a very large number of supernova remnants now in the GeV gamma ray energy band. And the majority of them are actually known to be interacting with molecular clouds through either the detection of different OH masers, or for molecular line broadening, or the detection of molecular lines that indicate a shockwave interaction with molecular material. And here is a very small sample of the ones that have been detected in the literature. It definitely has increased since I did this slide. So following this train of thought, we actually look at supernova remnant MSH1161A. I'll probably refer to it as MSH11 as it gets a bit of a tongue twister saying it too many times. But this supernova remnant is a mixed morphology supernova remnant. And it's characterized by its center field X-ray emission seen here from this Suzaku observation, which is actually thermal emission. It also has a partial radio shell surrounding the remnant, particularly in the west here, and it has patchy radio emission throughout the remnant here. It was actually determined through CO observations and radio continuum observations that the supernova remnant is actually interacting with the molecular cloud that's nearby. And this is actually highlighted by where the radio contours shown in here in green are actually compressed. So the molecular cloud is in that region down the bottom there. There is also a pulsar that is found approximately here, if I could extrapolate, called J1105 that is found nearby the supernova remnant, but it's actually not associated with the supernova remnant. But it will actually be very important for our analysis in the next slide. So this supernova remnant is actually found in a very complicated region of the sky, and this is actually quite evident when you look at gamma rays. For example, here is my gamma ray count map of supernova of the remnant and the emission around it, and one using 17 months of Fermi-Lat data, and you can see that it's just very busy, right? Very busy. One can see that right here is the very gamma ray bright supernova remnant MSH1162. You can also see that here there's a pulsar that I was referring to before. There is also something called the Lighthouse Nebula, which is an integral source just here in the position of that white source. And apart from all these known sources, there is a lot of Fermi-Lat sources, gamma ray sources surrounding the remnant. So this is quite important. This means that it takes a little bit of effort to be able to get the gamma ray emission from this. And so we must be careful about making sure we take into account all the emission from these surrounding sources. In particular, we have to worry about this pulsar sitting there, right? Unfortunately, or maybe fortunately, supernova remnants are not the only ones that produce gamma rays, so do pulsars. And so we actually need to make sure that we remove the contribution of the pulsar to the gamma ray observation. So the best way to do this is essentially just remove the contribution of the pulsar from the remnant, from the gamma ray emission. And the way that you actually do this is that you phase fold the gamma rays with a pulsar ephemeridus. I knew I was going to screw up that name. Alright, so essentially what this ephemeridus does, it kind of tells them the birth date and like its Facebook profile and the tax file number of the pulsar. It gives the characteristics of the pulsar about this. And so this is what we use, and we use one from the second Fermi-Lat catalog. So any of you can actually go and do this analysis if you wanted to. But one thing with that is that the Fermi analysis, this pulsar analysis, the description of this pulsar actually came out in 2013. But I'm actually using 70 months of data, which corresponds to June last year. So it's not valid for the whole data set. But we want to extrapolate across it. So we had to check whether this was actually allowed to do this. And so one way that we did this is that we checked in the literature to see if this pulsar glitches and that it's not included in the ephemeris. And we also checked to see if it was noisy. So what I mean is that when you look at the data outside the validity of our pulsar ephemeris, you want to see if this pulse profile that is shown here at the bottom, if the shape and the peak actually moves or changes. And luckily, it actually didn't. So it meant that we could actually quite successfully extrapolate it over the whole set of our data. I forgot to point out while I was discussing is this is actually the phase pulse diagram that we observe, and I have plotted 2 cycles of it so that you can actually see more of it. So now that once we've got this and worked out that we have successfully described what the pulsar emission is coming from, we now just literally cut the data. And so what we use is the off-pulse window, which is here highlighted in purple. And we use that for our for our gamma ray analysis, sorry. So using this newly filtered data, we now want to determine whether we actually see something significant gamma ray emission coming from the direction of our supernova remnant. the way that we do this is that we calculate what is called a detection significance map of our data. So you remember before how I said in the counts map that it was very complicated, the region. So to be able to calculate this, we actually needed to incorporate all those sources around our supernova remnant to be successfully able to work out if there's emission coming from there with that. So we actually did do this, and this is the TS map we got for this. I don't have a scale on it, I'm sorry. But what you can see is that towards the west of the supernova remnant, where I said that that molecular cloud was, we get a concentration of the gamma ray emission coming there. And it's detected with a 5 sigma detection. So quite good. I'm pretty happy when I saw that. Right? To make you guide your eye a little bit, I'm not sure how well it is to be seen there, I actually highlighted pink contours there, the location of the molecular cloud, and you can see it's quite coincident with what you expect with that. Another thing to actually take away from this is that we were able to actually successfully remove, 1, the pulsar, there's no emission in the position of the pulsar, and 2, the gamma ray emission coming from that very bright nearby supernova remnant. So it means that we can say with quite confidence that there is significant emission coming from the direction of the supernova remnant from this. So now that we actually have some significant emission, it's time to characterize the gamma ray emission we observe. So the way we do that is that we generate a gamma ray spectrum, and this is what's seen here down the end here in the black thing. I plotted the full non-thermal spectrum just so that we could do a modeling and make a thing. But in the end, down here is the gamma ray spectrum, and the black corresponds to the statistical errors, the red corresponds to the systematic, and the blue triangles correspond to the upper limits that we obtained for our gamma ray analysis here. In addition, I also plotted the radio emission that has been detected here in this light green, and I also calculated using the Suzaku observation that I'll talk about a little later, the upper limit to the X-ray non-thermal emission here. If you assume that the observed gamma rays associated with this remnant arise from the supernova remnant itself, we actually model this spectrum using pion decay, arising from an exponential power law of distribution of protons being accelerated by the supernova remnant shockwave. And this is actually plotted here by the magenta line with this. I also plotted the corresponding non-thermal bremsstrahlung, shown here in orange, as well as the synchrotron emission seen here in purple. Unfortunately, the inverse Compton scattering actually fell below the axis here. To be able to produce the leptonic emission, because we have no control on the cutoff associated with the leptonics from the X-ray or the radio, I had to assume that the leptonic, so the electron population had the same cutoff energy as the proton population to be able to produce this graph. So if one actually makes reasonable assumptions about the properties of the supernova remnant, so assuming 40% of the explosion energy goes into accelerating particles, one actually can use our pion decay model to actually constrain what the density of the surrounding medium is. That it's interacting with. Under this assumption, we actually derive a density of 9.2 per cubic centimeters here. But just keep that into mind for later. I've also listed what other parameters I got that describe the parameters that produce these models as well, but just mostly focus on the density result here. So you're probably going, okay, great, you fit it with pion decay, but there's something called inverse Compton scattering and non-thermal bremsstrahlung. How come you haven't checked that? Well, actually, we did for completeness. We wanted to make sure that we could rule them out. And actually, we didn't really have to do much work to do that. When we fit the gamma ray model, the gamma ray spectrum, to be able to fit it using just inverse Compton scattering, we needed only in electrons, so not protons, just in electrons, stuff that an energy greater than the explosion energy of the supernova remnant. So energetically, it's unfavorable, right? So you can rule that out. You could actually fit the spectrum using non-thermal bremsstrahlung using reasonable electron energies, but you actually require electron-proton ratio that is much greater, that is an order of magnitude greater than what you actually measure locally here at Earth and what you get from modeling supernova remnants. And so we kind of assume that this is probably less likely to be occurring there. So now that we actually have a density estimate, the next thing that we want to do, we want to test our model, whether we expect what we get. No, whether it makes sense, I should say, sorry. So the way we actually do this is that we go to X-rays to see if we can work out. Wow, that's quick. Okay, I'm going over time a little, sorry guys. I'll try to be quick, I'm nearly at the end. Okay, so now we want to use X-rays to be able to work out what the density is of the material surrounding so that we can compare it to our gamma ray modeling. So what we did is that we took a Suzaku observation and then extracted spectra from all these things here and be able to, and then model it using an absorbed non-equilibrium ionization model. So at the bottom here is an example of the spectra that we obtained from our observations. And usually this is very common for all the other regions that we extracted, minus a few little things. What we actually found is that when we modeled this, the bulk of the emission, so everything surrounded in the annulus and that little ear thing that I call at the top there, was actually described by a cool ejector-rich plasma that is actually recombining. While these two sections here are described by the bottom, the two closest ears to me, actually are described by a hotter one that is ejector-rich, but is also ionizing, not recombining. So this fact that the bulk of the X-ray emission in the supernova remnant is actually recombining is quite interesting because you actually don't expect this. You actually expect supernova remnants to be ionizing or under-ionized, right? And so in other words, the way to think about that is that this tells you that usually in a supernova remnant, you expect that the temperature of the ionization temperature to be much less than the temperature of the electrons. But the detection of recombining plasma actually tells you it's the other way around. The ionization temperature is actually greater than the electrons. So this actually implies that there must have been some rapid electron cooling occurring, though. And so this actually can occur in two main ways. So there is through the interaction of hot ejector with cold, dense surrounding environment, or which is called by thermal conduction, or via adiabatic expansion, which will occur when the supernova remnant shock wave expands into a cold, dense circumstellar medium. No, that's correct. Yeah, into a low from a low. Sorry, let me get this correct. When it expands from a dense medium into a lower density medium. And so you get adiabatic cooling from that. And when we compare our timescales that we expect for each one, we actually expect that adiabatic cooling is the more likely candidate because it's similar to the age of the remnant, while thermal conduction needed much older, bigger than the age of the remnant, so it's probably ruled out for that. So last slide, I promise. Right? So apart from being able to characterize the X-ray emission of the supernova remnant, we were able to actually work out what the density of the X-ray emitting plasma is, and these are the results we got. We got 0.09 to 2.33. If you remember that from my gamma ray analysis, I got 9.2, right? Which is much higher than what we get for our X-ray analysis. And this is actually very common. This seems to occur a lot in all gamma ray supernova remnants that seem to favor hadronic emission. What this can actually imply is that the supernova remnant is actually interacting with dense clumps of material that do not radiate significantly in X-rays. Or what's happening is that particles at the shock are actually escaping the shock and it's going streaming ahead of the shock and interacting with the molecular clouds in front further up and enhancing the gamma ray emission that we observe. So we actually expect that it's probably more likely that it's the shockwave interacting with cold, dense clumps of material because of the location of the molecular cloud. So I just plotted it again so that you could see it. But of course, we can't rule out that there's no particles streaming away from the shock and enhancing the emission. Maybe if we get a better Fermi gamma ray detector at some point. So because I'm over time, I will just leave my conclusions there, or my summary, and take any questions.
So we have some time for questions.
So quickly, in the gamma ray image you got, it looked like the emission was literally centered on the cloud, on the molecular cloud. So it's not happening on the skin of the. It's not a skin interaction, but actually has to penetrate the depth.
So one thing to be careful about Fermi is that the PSF is very broad, so we can't actually get a very good description of where it is. But yeah, it is slightly, the peak of it is off-centered, and this is actually a very common thing in a lot of the supernova remnants, and it's currently one of the things that we're working on to try to work out why it's always offset. But yeah.
It's always offset in the nature that it looks centered dead on a molecular cloud?
Correct. It's always offset. It's not always sitting right on the, like, where you expect the direct interaction, though. But why that occurs? Don't know. Yep.
Yes.
You mentioned the electrons are cooled in one of the last slides.
Yep.
So you're talking about adiabatic. What about synchrotron cooling? I mean, you have radio measurements which will actually give you magnetic fields.
Yes, but we don't consider that in this because we're only focusing on the X-rays, and we actually don't measure any significant synchrotron X-ray emission coming from the supernova remnant. So we expect that it's probably not a bit large fact in this. I think down here.
So, Enrico, you have questions?
So,
Alex.
at 9 particles per cubic centimeter, what would be the total mass in those relativistic protons?
Oh God, I actually don't know the answer to that.
Seems like pretty high density.
Yeah, it is a high density. I don't know what it is.
And
off the top
then
of my head.
multiplied by like gamma factors. So what's
No, that's the
also-
density of the molecular gas that you're interacting with.
Was it density of molecular gas or was it density of protons?
No, the molecular glass. Sorry, I should have been more explicit with that. Yep.
So when you try to compare the density of protons
Mhm.
of the molecular cloud with the density of electrons which you get from your X-ray heating, it depends on how you treat the abundance ratios of all the elements.
That's correct.
Do you worry that, maybe the answer is that, in fact, there's no discrepancies, but in fact, you've not really properly modeled the number of electrons per proton in these environments effectively.
That's actually something we haven't actually considered, that of course it could be a possibility, but it seems the consensus is that it's not such a lot. Like, it has to be a significant difference from what we have to be able to compensate for that discrepancy. So, yeah, it could be a possibility, but I didn't personally do it for this one, but I think in the community they don't think it's really...
I'm just thinking, if you purely ejecta-dominated and you have iron, you have tens of electrons. No? But if you have iron at solar metallicity, you have 10 to the 4 electrons. So try to understand the difference in the mixing.
Yes.
Makes a big difference.
That's probably something we should look at, actually, I think. It's a good idea.
And last question, Lorenzo.
The slide where you had the density and the 2 numbers on top, like alpha and the
Yeah,
cutoff
sorry.
energy.
The ones I skipped very quickly.
So, like alpha is the momentum spectral index, is that correct?
That is correct, of the proton distribution.
Okay, and the product cutoff is not very extreme. It's like just a few GeV.
Yes.
Can you sort of reconstruct whether this is a reasonable number given the age of the system and what we know from the acceleration rate? Because we think supernovae should be getting up to PeV, right? And
Yeah,
this
of
is
course.
like nothing.
Yeah, it's nothing. We could. I didn't do it. I should do it, though. But yeah, I see no reason. This is not really, like you said, it's not really doing too much here. But and it's also actually quite steep compared to a lot of other supernova remnants. Like, more gamma ray emission coming from other supernovae is a bit more kind of flatter and nicer. This one's quite hard, which is kind of interesting as well. But yeah, of course, it would be I think, a good thing that we should do for that.
And you have an estimate of the field from
The
the
magnetic-
synchrotron.
Yes, correct. I do here. So it's enhanced compared to what the magnetic field is in the interstellar medium. So that's how you get this. But that's a model parameter as well. So
Okay. Thank you very much, Katie. We keep going with Tombu and X-ray scaling regions of early type galaxies.
First of all, I should have said that for those who attended the last year Compton workshop, I have some duplicate material, but there are new stuff as well, so bear in mind. So, X-ray scaling relation. It has been investigated extensively for the last 30 years or so, ever since Einstein detected a lot of hot gas in the type galaxies. And I listed some of the early works here and then all that work. You can notice that there are quite a few people are maybe in this room. If not, then maybe in this building. If not, then they were here some time ago. Early days, the relation is based on the total X-ray luminosity and the B-band optical luminosity, and compare the two. And here's the one example, and I took just in one of the papers. As soon as they built this, it was quite obvious that there are correlation between the two quantities, but the scatters are pretty large. You can see that the scatter is almost 2 orders of magnitude, actually more than 2 orders of magnitude, so a factor of 100. That has been the long outstanding puzzle in the extragalactic astronomy. And there are some suggestions. So what makes that large scatter in LXLB? There are various candidates, some internal effects, some are external effects, including total mass, internal kinematics, some has rotation, others don't, and some has intrinsic flattening, others round, some has star formation episode, recent star formation episode, I should say. Then Asian and the supernova feedback, and the external effects may include confinement by the other ICM. Some of them are in the clusters, or info, merger, temperature stripping, and so on. Looks like all those effects should be involved, so it's pretty complicated. So we had to figure it out. So what would be the prime factor of that? So compared to the earlier work, advantage now is that we have basically 2 advantages, I think. One, we can measure the gas property much better than before. The main reason is, thanks to Chandra, we can detect all those point sources, can effectively remove them, so we can measure the gas properties pretty well. The second advantage is the baseline information of the early type galaxies. We know them pretty well. We know those rotation information, kinematics information, we know the shapes, and we know the stellar star formation episode and so on. So with those 2 advantages, we can do a little bit better job. So a few years ago, we started with looked at about 30 normal galaxies. Normal galaxy meaning not only selected by the Chandra, by X-ray, also we select by the optical line indices. In other words, which were well studied in the optical energy band. So by doing that, we include more gas-poor galaxies compared to the previous study. Previous study usually picked up the gas-rich systems because that's easy to study. But now we're looking at more general samples. And then instead of LX total, we use LX gas. And now the scatter is even larger. This is now order of 1,000 from the gas-rich to gas-poor. I show the blue lines. This is a linear line expected from the LMXV portion. So many galaxies, X-ray, the gas luminosity is even lower than the LMXV luminosity. And even worse, the order of magnitude lower, that's the active binary and the cataclysmic variable, the contribution, which is about order of magnitude lower than the LMXV. Some galaxies, gas luminosity is even lower. So it's getting trickier because you need to exclude all those guys, not just LMXV, also those guys as well.
What do the uncertainties correspond to? Is it only the measurement uncertainty, or does it also include the uncertainty in the determination of the A, B, and C?
These are basically based on the point sources are all excluded, and then based on the spectral fitting. You put actually to do this, you put the undetected LMXV portion, and then 2 components of CV portion, including the low end, the soft component and hard component, and then gas components. So 4 component model fitting. So that's how we detected the gas luminosity. For those guys, it doesn't matter because it's way low. But at the low end, you need to really exclude them well. Otherwise, your answer is going to be incorrect or having a large uncertainties. So that's one thing. And then another relation you can get is the luminosity and temperature relation of the gas. This is a gas-to-gas relation. it turns out that this is quite good diagnostics. I'm going to get back to that point soon. So that's the first study. And then we want to replace the LK with the total mass. We knew that the total mass is a much better important quantity, but it's hard to measure that. But in this case, we used the measurements from Dizon et al. They used the globular clusters, the planetary nebulae kinematics. This is a totally independent mass measurement. So, and they published about a dozen or so galaxies mass within the 5 effective radii. So we compare that. Yes, the gas luminosity is really strongly, tightly correlated with the total luminosity, the total mass. So that's we can confirm. The relation, it goes like the gas luminosity goes like total mass to the 3rd power. And if you plot the gas luminosity versus K-band luminosity, for example, here is the largest scatter. Now, this is a new stuff. We just submit the paper. We're now using the Atlas 3D sample. This is a volume-limited sample, and they have the multi-wavelength data. So they obtained virtually everything they can. So there's a lot of useful information for that, and detailed dynamical models available. They measure the rotation, shape, and on and on. And we select them with the Chandra exposure larger than 10K, and we found about 61 galaxies, and which actually doubled the previous sample and also includes 5 CDs. So here is the true relation. LX gas to the LK and the LX gas to the temperature of the gas. At first glance, it doesn't change much. But since our sample is much bigger than before, what we can do is we can study the scaling relation in the subsample of the galaxies, where we know their information pretty well. So here are it is well known that the Earth-type galaxies are two classes, so-called E dichotomy. The first groups are often called core elliptical galaxy. Core meaning the central light distribution has a core in the center, as opposed to power law cosmic. So those guys typically have large stellar mass and high velocity dispersion. And usually isophotes are round, and the stellar populations are old, so no recent star formation, and stellar kinematics shows they are slow rotator. And then the other classes are the opposite. All the properties are in the opposite. And the interesting thing is, core galaxies tend to have a large amount of hot gas. So people try to consider that the core galaxies may be formed primarily by dry merger. The core is the product of the gas-rich wet merger. The cusp in the center is can be interpreted as the result of additional star formation triggered by the recent merger, which in this case is a wet merger, and the other core galaxies doesn't have that. But that happened to matched with the amount of hot gas, so people can interpret that as the hot gas, hot ISM, may provide a quenching mechanism, so-called halo quenching. Star formation is quenched by the hot halo, meaning that the agent feedback, the energy input is going to be episodic. But given the hot gas there, it can absorb all the energy, store it, and smooth it out, so it works as a working surface. So hot gas, having the large amount of hot gas, can provide a quenching mechanism, which happen to be also matched with nicely the core galaxies, the first classes of galaxies. But the key question is, agent feedback may work to prevent the cooling and the star formation. But the more fundamental question are why core galaxies why those hold hot gas in the first place. And another interesting question may be, some of the core galaxies are gas poor. then that scenario is not working in that case. So, and those are the questions that we can address through this scaling relation. So here's the in the gas luminosity versus LK relation, I plotted two classes in different colors. Round galaxies are red here, and slow rotators are red, and older systems are red, and the core galaxies are red. Those are the first class that in the 2E dichotomy. So those guys are all gas rich. And the opposite one are more or less gas poor. But there are cases where even in this class, there are gas poor guys. In other words, some of the red points are down there, but not the other way around. There's no connection between the two. So none of the fast rotator would have the large amount of hot gas or so. That distinction is around 10 to the 40s. So let me get the same figure, this figure. I'm just showing that again. So here, the relation, again, the gas luminosity and the LK are correlated, and the entire sample, the relation goes like the LK to the third power. If you just use the core ones, which are all the red points, it gets steeper. It's going to be about 4.3. Those are the CD galaxies, 5 CD type galaxies. If you exclude them, that's going back to about the LK to the third power. I'll just make 2 points here. One, LK sigma square. That quantity often misleadingly used to indicate the gas luminosity. The reason being, through the mass loss, the stellar mass loss, LK indicate the stellar contents, and sigma square is indicating the mass injection rate. So that's interpreted as the gas luminosity, but that's not the case. In fact, the real relation goes like a square of this quantity. So Lx gas actually goes like this, the square of that. If Lx gas is like a Lk to the third power, then it coming back to Lk to the sigma force. That's the Faber-Jackson relation, basically. So it's all relatively all consistent, and this is kind of misleading to use that. And the second point is they are correlated, but still there's a large scatter. Even if you take into only the red ones here, which are normal core galaxies, still the scatters can be more than order of magnitude, and the RMS deviation is 0.5 dex, still large scatter. So one cannot use LK to predict the Lx gas. Now, I'm going to, this is the kind of main point here in my talk. The relation between the gas luminosity versus the gas temperature. This is again gas to gas. So all X-ray information. The 3 points, first, the correlates, in other words, excluding all the red points, then they don't seem to have any correlation. Practical statistical test says there's no correlation. And second, if you look at the red point only, they are tightly correlated from low end to the high end. And then CDs, the green lines actually taken from the O'Sullivan et al. 2003 paper, and that also goes nicely. They are shifted upwards. I'm going to go into these 3 points one by one. Those are the highlights of my talk. And here's a coreless galaxy again. Here I just excluded all the red points. And this is the coreless galaxies, and showing the X-ray luminosity versus temperature relation. There's no correlation. We can understand that because those guys are the ones which may have, some of them has a rotation, some of them are flattened system, some of them are even having a disk, stellar disk, and some has the recent star formation, and some has the cold gas. So those are all the mixed effects are playing there and work in coherently, so there is no obvious correlation. The situation is pretty much similar to the spiral galaxies in this case. So here's a comparison. Here's the spiral galaxies, the same plots. I took it from the Li and Wang sample, so almost no correlation. Multiple factors worked incoherently. Now, for the core galaxies instead, looking at those guys, the red point here, and those are basically represent the genuine elliptical samples. Those are passively evolving, meaning no star formation, the old system, sigma supported, meaning no rotation, and the non-CD normal galaxies, and genuine spheroidal. I further exclude few of them which may have some indication of the opposite properties. So these are the out of these, excluding few, these are the genuine ellipticals. Now I have the pretty tight correlation here. Those are the ones are really morphologically selected ellipticals, bulge only, old, dry merger, remnant, and slow rotator, no star formation, and on. And the relation goes like a temperature to the 4.5, 4.5. This is a pretty steep relation, very tight, steep relation. RMS deviation is only 0.13 dex. And that's from here, that's the low end, it is the NGC 3379, and the high end is NGC 4649. So that spans about 1,000 in LX gas. The large range, there is a tight, steep correlation between the gas luminosity and temperature. And if we take the M total goes like a gas luminosity to the third power, and the M total, combine the two, we get the M total goes like a temperature to the 1.5 power. This is basically Beer theorem. So what that means is these families of galaxies the gases are well visualized in the equilibrium. And now I'm comparing with that with the recent simulation, which shows that this is from I took it from the Negri and the Pellegrini et al. Paper, and they made they run the two-dimensional simulation, two-dimensional hydrodynamic simulation, and then they want to compare the difference between the sigma supported elliptical, basically no rotation, and the rotators with the fast rotator. And just so compare with the red points and red points, they are nicely matched with the observation. These are totally independent investigation, the observation and the numerical simulation. But that stops around 10 to the 40s here. And then there's one red point. They didn't actually study much, but that goes here. It's a nice relation, so an excellent match with simulation. Below that, that's kind of puzzle, because below that, the view is those guys are in states of outflow or wind. In that case, you don't expect the positive correlation between two quantities, because the hotter gas is hard to be maintained within the potential well. So you may have even anti-correlation in that picture. So something's wrong. That picture may not work here in this low end. So actually, I gave that's one of the few homework that I gave to Sylvia to think about. Hopefully they can come up with something. So now the third point is about the CDs. Those points are basically CDs, meaning that the central dominant galaxy in groups and clusters. And there, the gas luminosity is order of magnitude higher than here, goes up about order of magnitude. And again, the green lines are from the O'Sullivan et al. Papers. And likely the reason why they have a higher luminosity is related to their association with the groups and clusters. And having having those cities inside the groups and clusters, one can think about the dark matter and the ICM associated with the groups and clusters may work to have this effect by making the potential well deeper so that they can hold the ISM better and putting the external pressure from the ICM outside, and which make can help to confine the ISM. But the first effect may also change the temperature unless there is no additional cooling. From here to there, temperature doesn't change much. So if it works, then there got to be some additional cooling. And the second one may work without changing the temperature much. So, but we have only small number of those guys, so I added a few more well-studied the galaxies. Those are NGC 507, 5044, 7619. Those are well-known the dominant galaxies in the groups. So they are nicely fit in the same picture. But I have two more, and particularly NGC 1399. That is also known to be in the center of the phonics. So something is not right. But it may be related to the not just the total amount of dark matter. It may relate to how the dark matter is distributed. In other words, dark matter radial profile may play here. The clue may be found in the next slide, which recently Won et al. Observed the C2 emission, and the one group, those with the green squares have the extended C2 emission, and the other group has no C2 emission. And they found there is the entropy dichotomy. One is lower entropy, one is higher entropy. And the outside, excluding the central kiloparsec. And temperatures doesn't change. That entropy change is the density change, practically. So those green ones are in the higher density. So meaning it has better cooling because it have the higher density. So that's why it may have the extended the cold gas. And the other one is not working that way. That may work like this thing. And second clue, maybe, the Nagano and Matsushita studied the number of galaxies. They studied the dark matter radial profile. And what I have found is we have 6 galaxies in common, 3 in the green and 3 in red. These samples have more or less a similar mass to light ratio inside. Inside meaning about within the half effective radii. But if you go to the outside, this system changes, M over LK changes rapidly, and this system changes slowly. So meaning one has the shallow, the DM profile, the other one has a steep profile. In other words, one has a lot more DM outside rather than inside. And that's qualitatively consistent with the DM concentration index as a function of mass of the system. So it seems to be working fine in that qualitative way, but I think this is going to be a very excellent test case, both observationally and theoretically. Observationally, we want to measure that the radial profile, or the dark matter profile, and see really how much are they going to be different. And then theoretically, that change will really make this change without changing much in the temperature of the gas. It's already there. I'm almost done. I'll just advertise one new program we are working on now. The Chandra Galaxy Atlas, which is more or less related to what I talked today, maybe expand what we have been studying so far. We have about a dozen or so SAO, CXC scientists and the data system, the workers working on, and we welcome more volunteers and contributors. I'm sure there's a room for that, more contributors. And if anybody wants to join us, then feel free to come see me. And the main goal is we want to study the gas morphology in two-dimensional. So we want to study two-dimensional surface brightness. Not only that, we want to study two-dimensional temperature distribution, temperature map, and two-dimensional the metallicity map and things like that. So we can study, with that, we can study scaling is better, X-ray-based mass profiles, so community gas, and LMXB is a byproduct by doing that. And the major processing step includes merging the multiple observation. In some cases, some galaxies have been observed more than 100 times. So you have to merge it. It's not a simple step. And then we apply the two-dimensional adaptive binning. We are applying 4 different binnings, annulus and WVT, the weighted volume tessellation, which was what Deal and Stadler applied about several years ago. And our sample is now 4 or 5 times bigger than that. And then the contra binning and the E1's hybrid binning. I'm not sure whether E1 is here. And we are utilizing Hydra clusters. So having the multiple cores, the processing, the spectral expression of RMF generation, spectral feeding, these are the repeated same jobs that can be done simultaneously. So we get 50 to 100 to 1 performance gain. I will probably intend to show some figures like that. These are temperature map of the M60 and the M87, and with the 4 different the binning methods. But the time's up, so I will get back and bring this diagram as a summary. This is a schematic diagram that what I said today. Those are the 3 stops I mentioned, and there are 2 more in the larger scale, and they are, one can put them together, then this looks like this. I'll stop here. Thank you.
So we can take one very quick questions. One question.
So something that you didn't talk about is metallicity, the effects of metallicity. I mean, we know that there's a mass-metallicity relationship, but that certainly will affect the emissivity of the hot gas.
When you say mass metallicity, you're talking about the stellar mass metallicity, right? But
I mean, we don't know the gas metallicity as well. So the question
that's what we want to measure. Actually, there is a number of studies to dealing with the gas metallicity. That's what we want to measure. One of the nice things to have the adaptive binning, two-dimensional binning, is we pick the small regions, homogeneous regions, so we don't deal with the kind of problem like the multi-temperature issue in determining the metallicity. Because metallicity measurement is always depending on which model you apply and so on. So that's one of the advantages of having the two-dimensional, the spatial grid. So we hope that helped to sort them out. But we need the good statistics data for that matter.
Okay, thank you very much, Donggu. And I'll see all of you next week.